Because of the unfortunate time warp incident this morning, I want to make a few comments that are relevant to this upcoming exam. So firstly, I want to think about the following infinite series. I want to think about this infinite series. Since the terms are all positive and less than 1 over n squared, the direct comparison test tells me that this series converges, but doesn't tell me what it converges to. If I notice that I can do some algebra manipulation here, I can figure something out though. I can factor n squared plus 5n plus 6 into n plus 3 times n plus 2, and then I can do the method of partial fractions to determine the values of a and b. It's tempting to split that up into two infinite series and deal with them separately. That's legal to do only when both of the series converges, and in this case, neither one of them does, so that would not be legitimate to do. Instead, we have to actually look at a partial sum. This is an ordinary finite number of terms sum, so it is totally legal to split that up into two separate sums. These two sums are going to have some terms in common and some terms that differ. In the first sum, the first fraction is going to be 1 over 1 plus 2. It will be 1/3. The last number in the first fraction will be 1 over k plus 2. In the second series, the first number is going to be 1 over 4, and the last number is going to be 1 over k plus 3. In what I'm about to write down, I'm going to write down enough terms in both of these sums so that I can see which ones are in common and which ones are not. In the second sum, the last term is 1 over k plus 3. In the other sum, I had accidentally written n there, but this is partial sum number k, so it should have ended with 1 over k plus 2. The term before the last term in the second sum is 1 over k plus 2. In the second sum, the first term is 1 over 1 plus 3, 1 over 4. The next one will be 1 over 5. The next one will be 1 over 6, and so on. I'm going to underline the quantities that are going to cancel each other out. As a result, I can write down a formula for partial sum number k. The value of the infinite series, if it exists, is the limit as k tends to infinity of partial sum number k. As k tends to infinity, 1 over k plus 3 tends to 0. 1/3 is a constant. The limit of the partial sums exists and is equal to 1/3. We already knew from a comparison test that the series converged. This calculation shows that the value that it converges to is 1/3. Next, I'd like to use a comparison test to decide if this series converges or doesn't converge. Since the top and the bottom are both polynomials, when n is very large, I can think of the lead terms as basically determining everything that's going on. The lead term upstairs is n squared, lead term downstairs is n cubed. N squared over n cubed is 1 over n, so I'm going to compare this series to the harmonic series. If you remember how the limit comparison test goes, I'm supposed to take corresponding terms out of these two series, divide one by the other, take the limit as the index of the term tends to infinity, and see what I get as a result. If the limit exists and is positive, then either both series converge or both series diverge. So let's see. By doing the usual algebra, I reduce this down into this limit to look at. Cancel the n cubed out. If the limit upstairs and the limit downstairs both exist, and the one on the bottom isn't zero, it's legitimate to write limit of the top divided by the limit of the bottom. As n tends to infinity, 5 over n and 1 over n squared tend to 0. The numerator tends to 1 plus 0 plus 0, which is 1. 6 over n and 2 over n squared also tend to 0. The denominator has a limit equal to 1 plus 0 plus 0, which is 1. Both limits exist, they're both 1, and the one on the bottom isn't 0, so this limit is positive and finite. This tells me that my infinite series that I'm interested in and the sum n equal 1 to infinity 1 over n either both converge or both diverge. And we know that the sum 1 over n diverges. Therefore, this tells me that my original infinite series diverges as well. If I want to know the value of the sum n equals 0 to infinity of 2/3 raised to the n power, it might be instructive to write out some partial sums. Partial sum that goes with index 0 is just going to be 2/3 raised to the 0 power, which is 1. S1 is 2/3 to the 0 power plus 2/3 raised to the 1 power, which is 1 plus 2/3, which I'm going to write as 1 plus 1 times 2/3. And likewise for partial sum number 2, each new term when I pass from one partial sum to the next is the same as what I had previously, except I add in 2/3 multiplied by the previous term. This is a geometric series. That is something of type a plus a times r plus a times r squared plus a times r cubed, and so on and so forth. In this specific instance, a is 1 and r is 2/3. From our discussion in class, we know that such a series converges whenever the r is less than 1 in absolute value. The absolute value of 2/3 is 2/3, which is less than 1. The infinite series converges. For a geometric series, it's even nicer than that, though. We know what it converges to. When a geometric series converges, it converges to the beginning term divided by 1 minus this r number. That'll be 1 over 1 minus 2/3. You can deal with the fraction any way you like. This is 1 divided by 1/3, which would be 3. Or if you want to be a little bit fancier about it, you can clear the fractions. I'd like to figure out if this infinite series converges or not. Since both the top and the bottom are quantities raised to the n power, this suggests that it might be useful to use the root test. Since all of my terms are positive, the absolute value really doesn't matter to me, and e to the n divided by n to the n is the nth power of the number e over n. The nth root of the absolute value of an is the nth root of the nth power of something, the something being e divided by n. The nth root of absolute an is e divided by n. If you take the limit of that as n tends to infinity, the number on the bottom of the fraction becomes indefinitely big. The number on top is a fixed constant value. The quantities e over n become arbitrarily small as n increases. The limit equals 0. And since 0 is less than 1, the root test tells me that my infinite series converges. I'd like to apply our ideas of infinite series to calculate this integral as an infinite series of numbers. The observant will notice that there's a small problem with that integral in the sense that at x equals 0, the integrand is not defined. It turns out to just be a removable discontinuity, though, so for purposes of illustration, I'm going to ignore that issue. The thing that we're trying to integrate is not on our list of things we know about, and there is no easy way, or any way, to twist it around until it is, but we do know something new. From a previous in-class discussion, we know that if you select a given x number, if you calculate sine of x, it has the same value as the infinite series over on the right. I'm going to use the absolute convergence of this series in order to pretend I'm just working with giant polynomials, as we've mentioned many times in the past. The x to the first power terms are going to cancel each other out, and every term inside the brackets is going to have its sign reversed because of this negative sign. I want to calculate x minus sine x divided by x cubed. If you look at this series for x minus sine of x, it starts off with an x cubed in it. Therefore, pretending that it's a giant polynomial, I can write it this way. Continuing to pretend that everything is a giant polynomial, I'll divide the x cubed out, and I've actually got a power series now that represents x minus sine x over x cubed. To do the integral that I'm interested in, I'll pretend that everything's a giant polynomial and integrate it one term at a time. Having obtained my antiderivative, observe that when I evaluate it at x equals 0, all the terms are 0, so I can simply disregard that. Also, when I evaluate the antiderivative at x equal 1, x cubed, x to the 5, and in fact all the powers of x are just going to equal 1. So what I end up with is this. This infinite series is an alternating series. The individual terms decrease and approach 0, so this infinite series converges. Also, there's an obvious pattern to the terms here. Each term has a factor in the denominator that is the factorial of something. 3, 5, 7, 9, and then obviously 11 and 13 and so on. In the denominator, there's also another factor that is 2 less than the number that you're taking the factorial of. So if I wanted to, I could put a factor of 1 in here. 3 minus 2 is 1. 5 minus 2 is 3. 7 minus 2 is 5. 9 minus 2 is 7. 11 minus 2 is 9. The next one would be 13 factorial, and 13 minus 2, which is 11, as the other factor, and so on and so forth. Suppose that I approximated this infinite series by just stop adding after a while. What if, to get a numerical estimate out of this thing, I only kept the terms that went up to the 7 factorial? How wrong is my estimate going to be? We know from the general discussion of alternating series that the difference between this estimate, the one that stops at plus 1 over 5 times 7 factorial, that number, that estimate differs from the actual value of the infinite series by no more than the amount that I'm going to add or subtract when I do the next term. So if I calculate this minus that plus that, whatever number I get differs from the true value of the integral by no more than 1 over 7 multiplied by 9 factorial. Finally, using a calculator to do the arithmetic, the value of the integral is approximately equal to 0.163928514, and I know that the difference between that number that I just stated and the true value of the integral is no more than 1 over 7 times 9 factorial, which worked out to be 0.00000003968. So I should have about 6 or 7 digits of accuracy in my answer. 1, 2, 3, 4, 5, 6, maybe 7. We can say with a considerable amount of confidence that the integral is about 0.163928.